Chapter 14, Basics of Functional Dependencies and Normalization for Relational Databases. In this chapter, we'll talk about some informal design guidelines for relational databases, learn how to identify functional dependencies, and then introduce the concept of normalization and show how to progress through the different normal forms. So what is relational database design? It's really the grouping of attributes to form good relation schemas. There are two levels of relation schemas, the logical user view level and the storage base relation level. Design is concerned mainly with base relations. So what are the criteria for good base relations? We'll first discuss informal guidelines for good relational design, and then discuss more formal concepts of functional dependencies in normal forms. In this section specifically, we'll talk about functional dependencies. Here are the informal guidelines. First, the semantics of the relational attributes must be clear. Informally, each tuple in a relation should represent one entity or relationship instance. This is how we started to define things when we did ERD. For example, we had employees, departments, and projects, and we wouldn't mix their attributes in the same relation or table. In this way, only foreign keys should be used to refer to other entities. If you think back to the Hogwarts example, we had courses and students mixed together in the same table, with no foreign keys. Following this guideline, we would have separate tables that referred to each other using only the foreign keys. The bottom line is that we should try to design a schema that can be explained easily relation by relation. Then the semantics of attributes should be easy to interpret. Here's a good example, a simplified company relational database schema. If you look at each relation schema, you can see that the attributes pertain only to that entity. For example, if we look at the employee relation, we can see that in it we have social security number as a primary key. We have several non-key attributes, including the employee name, birth date, and address. And then we also include the department number as a foreign key, because a department can have many employees, but each employee can only work for one department. We mentioned previously that storing information redundantly is not good design, and we sort of alluded to that it does waste storage, but additionally what we're going to see now is that it causes different problems based on different updates that you actually want to do in the database. We'll take a look at, if you have repeated information, what happens in some cases if you try to insert new data, delete data, or modify data. Here's an example of an update anomaly. Consider the relation employee-project. Here we clearly have attributes from what should be two separate entities in the same relation. We have an employee number, a project number, an employee name, a project name, and the number of hours for that project. We might run into an anomaly when we try to modify information in this relation. For example, if we try to change the name of project number P1 from billing to customer accounting, this may cause the update to be made for all 100 employees working on project P1. If each P1 is different based on the employee that's working on it, then this is not something that we want to have happen. If we consider the same relation, we have an insert anomaly in which we can't actually insert a new project unless an employee is assigned to it. We also can't insert an employee unless he or she is assigned to a project. This is a problem because maybe we want to add employee information and they are new and they haven't started on a project just yet. Finally, in the same relation, if we delete a project, it will result in deleting all the employees who also work on that project because we're not storing the employee information separately anywhere else. Alternatively, if an employee is the sole employee on a project, deleting that employee would result in deleting the corresponding project. Mingling the employee information with the project information results in these types of anomalies. Here are two additional relation schemas that suffer from update anomalies. If the name of a department changes and that department's associated with multiple employees, it might be that you have a mistake when trying to actually update the department name, as it might not propagate to the rest of the records. Something similar would happen if you combine the employee and the project information. Here we have sample states for each of these relations, and you might be able to see possible deletion and insertion anomalies here as well. If we delete all of the employees that are associated with a particular department, then we're going to lose that department information. We should try to design a schema that does not suffer from insertion, deletion, and update or modification anomalies. And if there are any anomalies present, then we should note them so that applications can be made to take them into account. That is, if we have to store the data in a redundant manner. Additionally, relations should be designed such that their tuples will have as few null values as possible. Attributes that are null frequently could be placed in separate relations with the primary key. Why might we have null? Well, maybe the attribute isn't applicable, or it's invalid, or it's unknown, or it's known to exist but is unavailable. In the case of storing student information at a university, we do have to provide a middle name field, but not everybody has a middle name, so that might be null for quite a few students. The other issue of bad design is that it might result in erroneous results for certain join operations. What we want is Lossless Join. We want to use this to guarantee meaningful results from join operations. So relations should be designed to satisfy the lossless join condition, and no spurious tuples should be generated by doing a natural join of any relations. Let's talk about functional dependencies. We've seen these a little bit already, but here we're going to formally define them. Functional dependencies are used to specify formal measures of the goodness of relational designs, and keys are used to define normal forms for relations. So normalization and functional dependencies are very tightly intertwined. Functional dependencies are constraints derived from the meaning and interrelationships of the data attributes. We say that a set of attributes X, or an attribute X, functionally determines a set of attributes Y if the value of X determines a unique value for Y. Now this definition can lead to confusion, so what I'd like to do here is show an example and make sure that it's well understood. In order to do this, I'd like to call upon the idea of a function from mathematics. So you may have studied functions back in secondary school. What is a function? We say that something is a function when we can have the same y for different x values, but we can't have the same x produce different y values. So if we look at the examples below, on the left, do we have a function? If we pick any value of x, we see that we get one y value. It doesn't matter that both -2 and 2 produce 4. That's perfectly fine. We don't have any issues because none of the values on the left are producing multiple values on the right. In the right-hand diagram, we have something a little bit different. We see that we do not have a function because for the x value of 3, we produce 2 values. We don't have a unique value for the x value of 3. 3 leads to b and 3 leads to c. So in the diagram on the left, we can say that x functionally determines y, and that y is functionally dependent upon x. Here's an example of what that would look like in a very small table. Here we have a first and a last name. We have 2 people named Thomas, and thinking about what it means to be a function in math, we check going from left to right. Thinking about what it means to be a function in math, we can check a value for first, like Thomas, and we see that we get not 1 but 2 values. So if I choose Thomas, I can't uniquely identify a last name. So I know that first does not functionally determine last. But the other way around might be true. I may have a case where last functionally determines first. I choose a last name and I get 1 value. If I choose a first name, I might get multiple values. So we can say that last may functionally determine first. Here's the formal definition. So x functionally determines y if whenever 2 tuples have the same value for x, they must have the same value for y. Saying that x determines y specifies a constraint on all of the relation instances, so all of those records. Written as x with an arrow to y can be displayed graphically on a relation schema, and functional dependencies are derived from the real-world constraints on the attributes. Here are some examples of functional dependency constraints. Social security number determines employee name. If we pick a particular social security number, it will uniquely determine an employee name. If we try to go the other way, we might have 2 people that have the same name, but if we look up a social security number for both of those people, we won't get the same value. So the opposite does not hold true. We might also have project number determining project name and location, or employee social security number and project number together determine the hours per week that the employee works on the project. This is where the many-to-many cases come into play. You can see how you need two different attributes or more to functionally determine other attributes. A functional dependency is a property of the attributes in the schema, and the constraint must hold on every single relation instance or record in the relation. If you pick an attribute or a set of attributes and it is a key, then set of attributes or attribute can be said to functionally determine all of the attributes in the relation. We can actually look at instances or records and define functional dependencies. But in order to define functional dependencies, we have to understand the meaning of the attributes involved and the relationship between them. A functional dependency is a property of the attributes in the schema. Given the instance or a particular state of a relation, all we can say is that functional dependency may exist between certain attributes. We can't prove that it is a functional dependency, but we can say that it might exist. What we can definitively conclude, though, is that certain functional dependencies do not exist because there are tuples that show a violation of those dependencies. Here's an example of how we can rule out such functional dependencies. We look at this teach relation and each of the records in it. We can ask ourselves, if we pick a teacher, does that functionally determine the textbook? Well, if we pick teacher Smith, we can see that for Smith, we have two separate text values, so that is not a function. However, if we pick any text value, we do get a unique teacher. It doesn't matter that Bartram and Martin both determine Smith. Remember that that is actually still a function. Similarly, we can rule out that course determines text, because if we look, we have two cases of data structures. They determine two different texts. Now, if the texts were the same, we might have a functional dependency, but in this case, we do not. So we can say that the functional dependency text to course may exist. We actually can also say that text to teacher might exist. However, the functional dependencies teacher to course, teacher to text, and course to text are all ruled out because of the actual state. Take a look at the following mock table and see if you can figure out what functional dependencies might exist and which ones definitely do not exist. We're going to use this idea of functional dependency when we progress through normalization, so make sure that you have a good understanding of how it works.